So, what happens to drug molecule when it comes into bloodstream or into tissue? It can not only exchange between different tissues, it can also metabolize, change, undergo chemical reactions, change in its structure and composition. They are fantastically important for understanding toxicology and pharmacology of any chemical compounds. So general scheme would be drug at absorption site coming into body, and well, it can be excreted directly, but what we are interested now, it can be changed into metabolites, and then these metabolites in turn can be eliminated. We usually recognize two phases of metabolism. Drug undergoes phase 1 metabolism, may be activated, unchanged, or most often inactivated. Reactions here are hydrolysis, oxidation, and reduction. Then, after that, or sometimes just jumping directly, there is phase 2 metabolism, conjugation of drug molecule with different products, usually water soluble. Most often conjugated drug is inactive, but not always. Phase 1 often is catalyzed by enzymes from cytochrome P450 group. This is going to be unmasking of OH and an H group by hydrolysis, oxidation, and sometimes reduction. Phase 2 is conjugation reaction, for example, formation of glucuronide. Hydrolysis. Okay, let's look at cocaine molecule. Again, you can buy it 219 Hudson Avenue, Albany. That's next to State House now. It was in year 1885. So this is our cocaine molecule, and you see ester group and another ester group and also methylated nitrogen atom. This methylated nitrogen atom is relatively difficult to decompose, but it is easy to remove methyl group from this position or benzoic acid from this position. So as a result, we have benzyl ecogene or methyl ecogene molecule. A further loss of substituent results in ecogene molecule, which has no ester groups. Now, in human body, it is possible to ethylate this group, so you have coca-ethylene substituted. How important these changes are? If we look at what happens to cocaine in human body in different samples, you can see that only 30% of cocaine stays in blood. Most of it's benzyl ecogene, so methyl group disappears from you. In saliva, most of cocaine still is intact, but in urine you hardly see any of cocaine at all. You see or methyl ether or benzyl compounds, or sometimes you see ethylated group. In sweet, you still can see some percentage cocaine. Interestingly, most of cocaine is sitting in hair. So hair is a nice place where no metabolism occurs. But again, for example, in urine samples, you will see nothing. Same with different group of compounds. Heroin is double acetylated morphine. The reason of this acetylation is easiness of crossing blood-brain barrier. Now, with time, relatively quickly, one acetyl group is lost and further second group is lost. So, after crossing blood-brain barrier, heroin metabolizes into morphine, which is active form of alkaloid. After that, type 2, phase 2 metabolized, you have glucuronide of morphine. Another helpful way of metabolism in this group is metabolism of codeine. Codeine is opiate that produce very little morphine-like effect. It slowly loses methyl group, producing steady stream of low concentration of morphine. That's why codeine was widely used historically as cough suppressing agent and very mild pain reliever. It doesn't produce any adverse effect. Of course, what's problematic that it's very easy technically to remove this methyl group and substitute it with acetyl so to synthesize heroin. And this is the only reason codeine is not widely used in modern prescriptions. Next type, oxidation. Phenyl group can be easily oxidated to produce OH group, phenol. Methyl group can be oxidized to first alcohol and then benzoic acid. Amino group becomes hydroxylamine and then nitroso group. This type of reaction explains why benzene is very toxic carcinogenic compound and toluene is not. Toluene easily metabolizes in human body to make benign benzoic acid, which is quickly eliminated with urine. Benzene has no active group and it stays in the body for a long time and can produce carcinogenic effects. Another example of oxidative metabolism is alcohol oxidizing in human body to aldehyde, characteristic smell of drunk people, acetaldehyde, and then to acetic acid, benign compound. Disulfiram inhibits second step, so person who is drinking too much becoming mildly intoxicated with acetaldehyde, and this experience prohibits further drinking in some cases. Next group of metabolic reactions is reduction. Nitro group can be reduced to nitroso, to hydroxylamine, to NH2 group, opposite to oxidation reduction reactions we have before. Next, phase 2 metabolism. Its interaction with glucuronic acid, glucose with acidic group here, but it's not acidic group that reacts, it's this OH group, and it interacts with OH groups and nitrogen atoms to make glucuronide. This is glucuronide of morphine. This is glucuronide of nicotine and cotinine. It's alkaloid of nicotine group, and that's the mechanism. OH group interacts with another OH group, making glucosidic bond. Another enzymatic reaction is sulfation. NH2 groups and OH groups interacts with sulfur groups connected to ADP to make sulfamide and sulfonic acids. Here, for example, the complex drug molecule interacts with sulfotransferase, making active form, which is rather unusual, replacing oxygen here to sulfate. Conjugation with glutathione, it's amino acidic derivative with SH group here, results in compounds having RS substituted group. Then this residue disappears and you have mercaptor ether here. Glycine, the simplest amino acid, is very common in bloodstream. It interacts with many compounds of acidic nature. For example, benzoic acid reacts with glycine to make hippuric acid. Hippuric acid is commonly found in urine of horses.